Hello, and welcome to another of PAVE's weekly virtual discussions. I'm Ed Niedermeyer. I am the Communications Director here at Partners for Automated Vehicle Education. And I'm pleased to present a really fascinating subject for today's virtual discussion. It's one that really, I think, gets to heart of a lot of the deepest, most profound challenges in autonomous drive technology, and that is system level engineering and safety. And we have three wonderful guests here today to help us understand this, again, complex and really important issue. First up, we have Kartik Tiwari. He is the head of systems and safety at Gatik. Kartik, welcome. We have Robert Dingli. Sorry, Robert Dingli. He's the director of vehicle engineering at Plus. Robert, welcome.
Thank you.
And we have Steve Kenner. He's the Director of Safety Standards at Aurora. Steve, welcome.
Good, thank you.
So first of all, this is a topic that, from the outside, it's like, what's even going on here sometimes? And so I'd like to start by sort of asking each of you to share a little bit about sort of your work and what is it that you do, and sort of help us through that answer, help us understand sort of, what is the level of complexity that we're dealing with here on a systems level, and sort of why approaching this at a system level is such an important piece of what you do. Kartik, you want to start?
Yeah, of course, and thanks a lot for having me here. Yeah, it is definitely an understatement to say that autonomous vehicles, is a complex system. The way I think about this, and also talk to my team about this, is any system, like we actually use a lot of complex systems in our day-to-day life. Your iPhone is complex. The car you drive is complex system. But a group of individuals actually sat together and work together to figure out how to break that problem down into individuals' areas of specialization. And once you get to that level, then it becomes a day-to-day nuance, day-to-day product. Right now, we are in the process as an industry of going through that breaking down of the problem. It becomes really tricky because there are a lot of probabilistic components to this system, and that makes it a really, really hard problem to break it down. That is the fun thing and the most challenging thing of the system overall. I actually, just to give an anecdote, I actually compare this a lot to the space program, but with civilians involved. The design of a rocket ship had requirements from all the way from obviously the rocket design part, but also from logistics part as well, how to move the rocket components across the country. That is the level of things that we are actually looking at. When we design our system, we have to not only make sure how to drive the system on the road, but also how to do how to interact with the traffic police when they ask the system to pull over on the side of the road. How to do, in case of trucks, how to do roadside inspection, how to put up the hazard triangle on the road. These are things that have to be looked at. So there are a lot of moving parts, and all have to be thought of while we have to design the system.
Absolutely. And Robert, can I get your perspective on this as well? I mean, yeah, the complexity that he was just describing, it's not just the system itself, but it's also the development process is sort of part of this big puzzle.
Most definitely. It's a problem that we can't just tackle as a single entity. It has to be broken down, and systems engineering and accompanying processes allow us to dissect the problem and tackle it in manageable chunks. And then from there, the development process has to be adapted for each of the chunks that we're talking about, whether that's an AI system or a more deterministic control algorithm or whatever. We need to go through a process of figuring out what questions we're trying to answer, defining those requirements, and having a structure in place to be able to cascade those requirements through to the development program, and then of course test and validation, and then closing the loop on the development process. The problem itself is actually surprisingly technical. Humans are very, very good at driving, but getting a computer to drive a vehicle is quite complicated. And I guess in my career, I've been lucky enough to be able to follow the most technically challenging aspects of automotive development over the last 20 or so years. And it's only the last 5 years, I guess, I've been able to move into autonomous vehicles and ADAS, and that's been personally very rewarding because it is technically challenging, and there's a huge sense of achievement in being able to improve safety and process.
Yeah, and Steve, you know, how do you approach this issue of system level safety at Aurora, and sort of how does the complexity of these systems sort of shape how you approach it?
Well, certainly it is a super challenging problem that also makes it super fun and exciting, you know, to work on. So for sure, there's so many areas of technical competence required that you need to have the right technical expertise, right? So we're at Aurora, we're trying to make sure we've got people with a variety of different areas of expertise, multidisciplined, you know, areas. So people that understand safety critical systems, and then all the elements that they already talked about. And then it has to be like a holistic approach, right? You have to begin with the end in mind, and what you're trying to accomplish as a whole, and then be able to break it down into, you know, manageable chunks. And then the other challenge, of course, is that while anything that has a potential safety consequence is highly regulated, for emerging technologies, right? You know, certainly the automotive industry and some of the other industries that are safety critical, you know, are highly regulated, but that's emerging, right? So right now, there's also a lot of work of trying to figure out what are the right standards to work on that might inform the development of future regulations as well. One of the fun facts that you know I like to bring up, and this is just generally true, right? Is if you look at lines of code, you know, if you look at something like a Chevrolet Volt from like 10 years ago, it has about 10 million lines of code. Space Shuttle, 40 million lines of code. You know, a current high-end car that has all the active safety features might be as much as 100 million lines of code. But for an autonomous vehicle, right, they're saying it's going to be, you know, in general, an order of magnitude above that, right? Just that it's a way to sort of look at the technical challenge versus some of those other things.
Yeah, no, that's amazing, amazing context. And so what's amazing is that it's not just a system, but it's a system of like technologies that are all, you know, not all, but many of them are quite new, right? New kinds of sensor modalities. And so Kartik, can you help us? How does that affect AV development, right? Where, you know, you're trying to create a safe system sort of holistically, but then within that you have stuff that's just constantly changing all the time, updating, and whether it's in the, you know, the AI side or like I said, the sensors. How does that sort of impact, you know, dealing with this as a system?
Yeah, absolutely. So I think that there are a few different aspects of it. It's obviously a really, you know, loaded question, but there are a bunch of different aspects to this. The first thing is, I mean, you touched up on sensor modality. So the idea behind sensor modality is that we don't have a perfect sensor, similar to how we don't have a perfect component, and we need to have and that essentially from a systems design perspective and from safety perspective as well, forces us to and pushes us in the direction of balancing it out with like one shortcomings to with you know the strong points of advantages of some other modalities. And that's actually something that is that has to go across the whole system. It doesn't just stop at the sensor level itself. It goes across the whole system. And like to be more generic about this, it actually goes across the whole organization itself. There are shortcomings of the system itself that are balanced out by the operations. By the operations team. There are shortcomings, and the shortcomings is a pretty like harsh word, but that is how we have to look at it, because at the end of the day, we need to deploy a safe system that actually provides a business value to not only us, but also to the customer. And because of that, we have to take care of all these balancing, and to Steve's point, we have to take a holistic approach to this. A lot of standard, although there are no explicit standards that exist in terms of safety for autonomous vehicles, and that is what we all are working towards. But there are just very basic principle-based safety approaches that have worked for similar things, similar applications before, like for the last 100 years or so, that we can take inspiration from and try to deploy some of those experiences in this.
Yeah, and Kartik, I'm sorry, Robert, I want you to. Kartik just mentioned sort of this issue of, you have to sort of make up for shortcomings in different areas. If a sensor has a shortcoming, you have to make up with it in other parts of the system. That seems to be a really fundamental part of approaching AVs as a system, right? Is that
yes,
understanding the shortcomings and making up for it.
Definitely. All components within a system have their limitations. You need to know what those limitations are. You need to be able to detect when they've reached their limits or about to reach their limits. You need to detect when they fail. And then you need to have a mitigation strategy for each one. So it may be you have a redundant system, and maybe you, if it's a driver assist system, then you need to notify the driver that the feature may not be available and to ask them to take different action or so forth. And so this mentality of asking yourself what could possibly go wrong and how do we deal with it is almost a cultural thing. You need to do that in the design of the product you do, but you also need to do it in the testing procedures, the operations, and so forth. Humans inherently do this all the time. They may not consciously be thinking about how they're trying to detect failures and mitigation, but you'll find humans can react very, very quickly when something out of the ordinary happens, and our computer systems have to do the same thing.
Yeah, and Steve, how does this work? In terms of obviously individual sort of subsystems or components have to be validated, in and of themselves. You have to have a high level of confidence in that, but then you also have that system level analysis as well, right? Sort of how does that interplay work in your work?
Well, so let me comment on two aspects of that question, right? One is for sure going back to the question about sensors. I think in general, an approach that we're taking at Aurora is trying to get as much information as we can, meaning that we're trying to use the state-of-the-art LiDAR and cameras and radar, right, to get as much information as we can, knowing, as Robert said, that there's strengths and weaknesses of each of those things, right? So a couple of examples there is, one is if there's uncertainty in the perception about the ability of the system, for example, to tell the difference between, a person who is, walking a bike versus riding a bike, right? Then maybe you have to make the worst case scenario assumption, the longitudinal velocity of the bike and the lateral movement of a pedestrian, for example. And then the second thing is, if you look at how most people approach, for example, like the ability of a camera to recognize faded out lane markings, right? Instead of using the cameras to detect lane markings, you might use sensors for your localization system so that you know where you are on an HD map. And then you use the HD map to tell you what the lane boundaries are, is an example. So you have to think through those things to figure out, knowing that, you have to include sort of this safety critical thinking, up front, right? So for other industries, that are safety critical, defense, nuclear, medical, aerospace, right? Generally there's two approaches. One, they mentioned, system engineering process, right? So you start with what are you trying to do from a product perspective, and then decompose those requirements all the way down. But then on the other side of it, right, you have to start from, like unit testing to component to modules, subsystems, and systems, right? And then all of that, you have to say, what's the strength of your, test plan, and what verification methodology are you going to use, and what's the acceptance criteria? How much coverage do you have? How much sufficiency? How much inclusion of, let's say, high risk but low exposure items are included in that overall test plan, right? So following that system engineering process to decompose requirements and then go through the right-hand side of the system engineering V to go through the verification and validation process, I think is a sort of common element amongst safety critical industries. The second thing that you'll find in those same industries is actually the use of a safety case, right? So if you're trying to build an argument that a vehicle is acceptably safe to operate on public roads, you then want to be able to then decompose those claims and then have evidence that supports those claims as a part of being able to prove out the total system that you've done all the comprehensive things. And that again goes way beyond only the technical part. It includes, all of the holistic elements and the external environment in which we're operating and so on. So that, I think that's an important way to think of it is look at the system engineering approach and the safety case to sort of, help guide you to make sure you're doing the right things in the right way to prove out, this evolving technology.
Yeah. And I think we've been kind of circling a question that is really easy to sort of leave unasked, I think, but I don't want to, because I think it kind of gets to the heart of a lot of the things we're talking about. But the question is, why aren't AV simple? Like, why do they have to be complex? And I think we've hinted at some of this in terms of the balancing the system and things like that. But I think, there's still sort of, and we've seen a number of companies try to develop AVs and sort of not simple, but like simpler certainly in terms of hardware, right? So less sensors, even things like end-to-end, autonomous driving, learning systems, right? Where it's all happening, or the vast majority of what happens, takes place inside of the AI. Kartik, why do AVs have to be complicated? Why can't they be simple?
Yeah, actually, so there are two aspects to this, and this is actually, I mean, it's not even a question that we should like beat around the bush of. This is a really genuine question that I mean, we all ask ourselves, and just at a high level, the reason why a lot of people have like sort of evolved into talking about constrained ODD, your design domain or the use case is essentially to make the problem statement simpler for everyone involved, and especially for the business. Now, does that actually work for the business? That's a separate question that has to be asked. But that is at the heart of this. So there are two specific things here. One is the actual design of the system itself. Why can't it be actually simple? And the answer to that is, at the end of the day, we are dealing with a noisy environment. And when I say noisy environment, I mean, the weather fluctuations, the position of lighting, and the unruly infrastructure that exists on one end. And on the other hand, we have the noisy participants in traffic. So you have pedestrians who are like highly unpredictable. There is a level of predictability, but they are highly unpredictable to different kinds of drivers that you encounter on the road. So we as humans are actually really, really good at predicting this, and that is like actually the ultimate problem that has to be solved by all the systems. But that is the basic reason why deploying in real world conditions on public roads is we have to get over those problems. If we try to reduce some of those parameters, some of those variables, then we are now again talking about constraining the system on we get down to industrial robotics, for example, where we only have deployments in private spaces, or there is a lot of talk about dedicated lanes where only the automated vehicles can drive. So that's the system design aspect of this. At the end of the day, all of this actually still lead to the safety case as well. And the safety at the end of the day, we can talk a lot about standards and everything, but at the end of the day, safety is about trust. and you can only there is a subjectiveness of trust that comes with us as people, as everyday people, trusting a system versus a policymaker or any other stakeholder that is heavily involved in or has a vested interest can trust the system. So to do that, we have to like Steve's point, we have to have a safety case. We need to make sure that we present to someone who is not developing a third party and say that, okay, this is what we want our system to do, and this is how we manage to do it. The problem with that, now coupling it up with the system design, the probabilistic nature of the problem and the solution, is that because there is a lot of probabilistic components in the system, it becomes harder and harder the more probabilistic the solution is to actually give a clear-cut answer that this is what the safety, this is how we prove our safety case, apart from just regularly driving for billions of miles in simulation and in real world. So that is why the system is complex. One analogy that I do give in this is we have face, detecting someone's face is a technology that exists. It's an afterthought on Facebook. It's a bunch of different apps that our phone has face detection technology. But suddenly, if the exact same algorithm is used by, I don't know, like Department of Homeland Security for screening, suddenly the impact of that becomes way higher. So developing a technology that can drive itself, what we call in this industry as demoing our system, is relatively easy. But making sure that it actually matches up to what is expected to show that trust is a pretty high bar.
Yeah, Robert, I can see you want to get in.
Yeah, I just want to add to that. Kartik's made some really, really good points. And fundamentally, driving is a difficult task. Humans have to be very good at it. Roads and motor vehicles, traffic signs, everything's designed around humans and the human perception system, mainly eyes and ears and so forth. So we have to adapt the technology to match the environment and the scenarios and the job task of what a human is very, very good at. And we should never underestimate how successful humans are at successfully doing that task. In the USA, I think typically there's between 35 and 40,000 fatalities every year. 40,000 too many. There's no argument there. However, given that there's over 3 trillion miles driven every year, that's in the order of one fatality. No, so one fatality accident per 100 million miles of travel. That's a very rare occurrence when by anyone's standards. It still happens way too often, but it's a very rare occurrence. So comparing that to existing methodologies around robustness and reliability of components that typically go into motor cars, there is a target of 6 sigma, which is in layman's terms approximately 1 billion components. But one failure in every million components is nowhere near good enough to give you the level of reliability that humans have. So we need to be much better than existing standards and existing processes when it comes to the approach to safety. That's what makes it very, very complicated.
Yeah, the other thing I would add, I mean, certainly in spite of it being rare, none of us would view the current toll on human life as acceptable, right? And one of the exciting parts about doing this is to be able to deliver the benefits of self-driving technology, and which is part of our mission, right? Because it's the benefit side that makes this sort of a passion for all of us, because of the potential to change those numbers, right? But the complication is real, right? So trying to simplify it, if you for example, say, I'm going to use, machine learning to be able to simplify it, right? Machine learning is certainly used to train how to classify detected objects, right? However, you know, the ability to recognize that it's a person sitting on the side of the road is completely different than knowing that 1 second after you recognize that person, they're going to stand up and walk into the road, right? And another example is, you know, hey, if you recognize a soccer ball rolling into the road, well, that's, you know, again, 10 years ago, that was, you know, maybe not possible to do. Isn't that awesome? But that's completely different than knowing that likely a child is going to chase that ball into the road, right? So those are some of the things that also, you know, make it incredibly challenged that we as humans, you know, are able to learn, you know, as experienced drivers.
One of the things that I, just to add one other thing, that I use at least internally to talk about this is solving the, you know, the automated autonomous vehicle problem is like very much solving a safety critical Turing test problem. That is exactly what all of us are trying to do. Now, there are different ways and approaches to solve that, but that is the essence of what we are doing. And that's why it's really complicated and hard.
And tying a couple of those thoughts together, I've recently had the experience of teaching a couple of teenage children to take their first steps driving. And one thing you realize, having come from this industry, is that the big problems we have to solve, perception, prediction, they're the hardest problems for computers to grapple with. They are the problems that humans deal with very, very well. Even with zero driving experience, and a teenager can detect that that's another motor vehicle and they're traveling in that direction. They can detect the soccer ball, they can detect the child walking along the sidewalk. So humans are very good at the problems that we are, which are our biggest challenges in the industry. And then the flip side to that is that the planning, the control, actuation is something that we can be more deterministic about through computer control than perhaps what a human can. And humans have to learn that response from the system. So it is a very complicated task. Humans happen to be very good at it.
Yeah, absolutely. And, you know, we were talking earlier about sort of how at a system level, you know, things balance, you have to balance things out, right? If you have a challenge here, you have to make up for that somehow so that at the system level, you do have that confidence in your safety case. Kartik, can you give like some examples maybe of how that relates to the challenge of probabilistic AI specifically, and sort of even maybe how do you even validate a probabilistic system, you know, so that you can have that confidence?
Yeah. Yeah, that is the, you know, the $1 million question for sure. Or, you know, in this case, maybe trillions of dollars of question, worth of question. But the way, and this might actually relate to one of the other questions that you asked earlier. So at least like internally at Gatik, the way we try to divide the problem statement, at least is or at least the testing of our system is we have knowns and we have unknowns. Whenever we get to know that a problem exists or a scenario exists that is challenging, we need to make sure that it is registered in the the conscience of the company and the overall experience of the company, by including that in our unit testing to component testing, hardware in the loop testing of our system. Whenever a new change is injected into the system, it goes through all those existing failure cases that we know of. The one sort of unwritten rule within Gatik is that we want to go out and test on a system level, like entirely within our ODD, only and only to figure out those unknowns. Now there are bounds that we want to make sure that exist so that we can safely test those systems, but that is the reason why on-road testing exists, and that's why we have to we want to make sure that we fail within in a very protected bubble of having an AV or of having a safety driver in known conditions. so that when we eventually take the person out of the vehicle, we have very high confidence of the system actually not failing, or like even if it fails predictably and gets to the minimum risk condition.
Yeah, Robert, do you want to add to that?
Yeah, sure. Driving scenarios in general can be described as stochastically as very long tail distribution. That is, unusual occurrences occur quite frequently, or things that are that you may not have seen before occur quite frequently. Again, humans are very good at detecting that and dealing with it. But if you have a system that's trained on a particular set of experiences or set of data, then that system has to be able to generalize to scenarios that it may not have seen before. So how do we deal with that? One is, firstly, we make sure that the system is trained with the largest data set we can get. And in pluses, in the case of plus, we have a roadmap to be able to collect relevant, statistically significant amount of relevant data of both ordinary driving cases, but also corner cases over a very long period. In fact, we've publicly stated that we believe it's going to take billions of miles of collecting data for us to be able to build up that data set for both training and validation. We've got a roadmap to do that. So it sounds like an impossible number, but we certainly have that in our plan. But the second point to make is that once you have trained the system and it's able to handle the scenarios that you've taught it to handle, and you've got very high confidence in that, you also need to be able to train it to detect when it's in a scenario that's beyond what you've trained it to do. That is, it may be an operational design domain ODD issue where perhaps the weather has changed, perhaps a camera has been blinded by a bit of dirt off the road or something like that. The system has to be able to detect that and then continue in a safe manner. It may be that it has to pull over on the side of the road. Maybe it has to continue at a reduced speed and take a little bit longer to get to where it has to go. In the same way that a human might, right? If it starts snowing heavily, you might want to slow down your car. Obviously, in the case of our trucks, if we detect that, we'll do a similar thing. And to the extreme, we may have to just pull over if we do not have confidence. So, it's about capability and responsibility. Once you've determined that the scenario may be beyond your capability or on the verge of being beyond your capability, you're responsible for making sure you put the system into a safe state.
Yeah. And Steve, I'd love to get your thoughts on this validation question, but maybe you can roll it into the role as well of standards in all this, right? It's a big focus for you, obviously, and when you have, again, like probabilistic systems and not probabilistic standards, right? The standards are pretty clear. Reconciling those must be quite a challenge.
Yeah. So let me say, so in terms of validation, generally we take an approach of trying to do, not trying to do, we actually do a mix of simulation, track testing, and on-road testing, and certainly the on-road portions are really, it's a lot to do with the the quality of the miles and what you learn from them, because it's an important element, but in many cases you're looking for like the exposure to some of the rare events and coverage and things like that, so we take that holistic approach. We do all of those things because, like the other things we've talked about, there's strengths and weaknesses of those, and I think together they help a lot to be able to understand it. And then the other challenge with on-road miles would be that concepts like change management, right? You have to figure out, if you change hardware or software, you don't want to then run a bunch of on-road miles to be able to then revalidate, right? You want to be able to have an efficient way of going about, doing that with, high confidence, right? So transitioning into standards, actually, there are quite a number of standards that, let's say, people are using, today that are, somewhat responsive to autonomous vehicles, even if they weren't intended. So one of the ones that actually refers to what Robert was talking about is the functional safety standard, ISO 26262. And while it doesn't include machine learning and was developed considering a driver in the loop, there's certainly some really great concepts and techniques that you could actually adopt to autonomous vehicles, over time. And the nice part about standards is that not only can that help an individual company understand what they need to do, but it raises the bar for the whole industry, right? And so in my team, we're committed to doing that at Aurora, to participate. So we're participating in the automated vehicles safety consortium. We're working with UL, working with some of the various SAE standards and other ISO ones. So there isn't a silver bullet, to be sure, but I think working on those is really helpful. Not only does it help raise the bar for the industry, and a part of being committed to collaboration and transparency in this emerging industry, where we're at is nothing new, right? Having a new technology being developed without standards in place is very similar to all the other automotive safety technologies since the automobile was invented, right? And then standards come, and then guess what? Then the call for regulations comes, and so best practices generally inform standards, and then standards inform the development of new regulations, right? So and in that whole process, trying to make sure those things capture, the safety that we're trying to be able to do for the entire industry and raise that bar, will then also help with the confidence and trust that others talked about, right? So for sure, getting trust from regulators, other government organizations, non-government organizations, and the public, in part, can be informed by that sort of transparency and collaboration of the industry working together to do those things. So I think it's really a great initiative. It's exciting, and again, quite frankly, it's one of the things that helps some other technologies, the predecessor of autonomous vehicles, to then be as pervasive as they are today, and in some cases, helping to be building blocks on the platforms that we're using to develop our autonomous vehicles.
Kartik?
So I actually completely agree with what Steve said, and there actually needs to be a huge push. I think there is already a huge push to make sure that there are standards. But just pointing out a little, some of the challenges because of that. One of the things that we sort of hinted towards, but definitely plays a huge part, is the operational design domain, or what we have been referring to as ODD. Definition of the ODD actually plays a huge role in how the standard affects it, and even like building off that standard. That in effect is where it relates to our safety case. When we go out to any external stakeholder and talk to them about this is the ODD, or this is the safety, our safety case, it has to relate to the ODD that we want to work in, and how do we know that we are within the ODD versus not, and all of those things play in like building that standard as well. A classic example that I use in this is we can actually defining an ODD is actually really tricky, because we can intuitively say that yes, even us as people, we can say that we are it is tricky for us to drive at night, but we can drive it in daylight. But at what point during dusk or dawn do we say that okay, right now is the time for us to pull over to the side of the road? That like defining those things are tricky, and it is going to depend a lot on different systems, specifically how they are designed. So at the end of the day, the standards are actually going to help in getting a common ground, and also making sure that we can have some level of apples to apples comparison, because that is also a huge debate that we need to have, that okay, how do we define that? Because at the end of the day, when we talk about deploying this with we need to have the general public's consent to deploy this and have them on board. And if we cannot go about giving a statistical description to a person to let them know that okay, this is actually a safe thing, we need to condense it into something that they can trust, and standards are the right way to do it. The only one thing that I would mention here is at the end of the day, it is going to be a holistic approach. People who design the system have to be an integral part of designing the standard as well, and at every level. And as Steve mentioned, this is part of how standards developing and designing standards has been happening for a really long time, and this is not going to be any different.
Robert, any thoughts on standards?
Yeah, it's very important that we as a society have confidence in the new standards serve as a metric, if you like, for defining requirements for performance and for validation strategies and so forth. On top of the standards, here at PLUS, we're working with a lot of the regulators or potential regulators going forward. So whether that's federal or state departments of transport and local authorities in all the areas that we aim to be testing over the next few months or next few years. Working with these regulators helps them define what perhaps role they need to play in either setting the standards or setting the regulations moving forward. As Steve said, there are some existing standards, and these standards we're talking about are actually not regulations. They're just but they are considered best practice. They're not necessarily applicable to every aspect of the autonomy challenge, but where they are applicable, we certainly apply them. So, for example, functional safety is very applicable when it comes to the more deterministic part of our software stack and the actuation, even a lot of the sensing task itself can be evaluated and defined, have requirements defined by the functional safety standards. However, as Steve said, when it comes to machine learning, or the fact that there is no, the long-term plan is to have no driver in the vehicle, there are some deficiencies or lack of applicability with the standards. However, we can still apply them where they are relevant, and we can also learn from the underlying thought process there. That is defining requirements and making sure there's a validation case behind every single requirement, and having a cascade of requirements and traceability between all the requirements. These are underlying engineering principles that existed long before functional safety came along. They've been enhanced by functional safety, and of course, the underlying principles that we adopt every day in our industry.
Absolutely. And, we're just about out of time, but I do have one last question, because I think it really kind of sums up a lot of this, and that has to do with culture and the role that culture plays in this. And I know it's a tough question to maybe answer in a short amount of time, but if you can keep it short, that's great. But yeah, when you're dealing with this level of complexity, how important is culture? Kartik, you want to start?
Yeah, culture is really, really important. As I mentioned before, part of solving the problem of a complex system is to break it down into smaller, more digestible chunks as an organization or as a group of individuals. While making sure that we are, this is sort of the necessary evil of systems engineering, that we have to break it down to solve the problem, but we also cannot lose the North Star. We need to still see that everyone has to keep an eye on it, and culture. To keep it short, the culture is a very, very important aspect, because we want to make sure that we are breaking the problem down while also making sure that everyone still knows what we are overall solving for, so that we don't end up in like local minimas. Like we don't just create the best perception algorithm while not actually making the system driverless, because that is a slippery slope.
Yeah. Robert?
Yes, certainly. Culture is super important. In fact, the way I try to describe safety and safety engineering is it's as much a cultural problem as it is a technical problem. Making sure that everybody that's in a role that contributes to a safety critical system understands their roles and responsibilities there, then makes my job, overseeing that process much easier. If everybody understands that they need to ask themselves the questions, the safety relevant questions up front, and add those requirements into their development program, then safety becomes inherent in the design process, the validation process, and so forth. It's not a separate, it's not a separate layer on top of the engineering process. It's built into it, and then it becomes normal for people to consider all of these cases, scenarios, failure modes, etc., in their design process. And then it just the culture shifts from am I doing am I ticking the boxes for safety, or am I making a high performance system where the performance is defined as meeting safety requirements along with all the other requirements. Okay, so the culture is super important. On top of that, there's another aspect to the test and validation that we believe at Plus, and that is that we try to, whilst we strive for individual responsibility, we also strive for a level of independence when it comes to the system level testing. So defining test cases, executing tests, and providing the feedback is something we try to separate from the engineers who have a vested interest in the performance of the system. So in doing that, we ensure that there's multiple layers of ticking the boxes to make sure that we have a system that actually performs the way we think it should perform.
Yeah, built-in accountability. All right, Steve, last word on culture.
Yeah, so for sure, safety culture is foundational, right? Matter of fact, I'm not sure you can be successful in this industry without a strong safety culture. It has to be a part of everything you do, from grounding policies to ability to, write safety concern reports and have them, addressed appropriately. Yeah, I've often said, safety is the ultimate team sport, right? Like literally everyone has to own safety, from the CEO down to everyone else baking it in to every single thing they do. So I think it's foundational. I think one of the things that is happening also that might be related to a standard is a safety management system, where people are defining organizational safety policies, a safety risk management process, safety assurance, and safety promotion that are all influencing and a part of then the fabric and culture of the organization. So I think that's a great thing to end on, because I think it's really, essential in this industry, and it's not just the culture of the companies, but it's the culture of this industry that we're all a part of.
Absolutely. And we have gone a little bit over time, but I think everyone will agree it was well worth it. Thank you to our audience for signing up and for attending a conversation about a topic that I know can be quite intimidating, but especially thank you to our guests for taking such a complex topic and making it comprehensible. Could not do this without you. Kartik Tiwari, Head of Systems and Safety at Gatik, thank you. Robert Dingli, Director of Vehicle Engineering at Plus. Robert, thank you so much.
My pleasure, thank you.
And Steve Kenner, Director of Safety Standards at Aurora. Steve, thank you so much for sharing your expertise today.
Yep, and thank you all.
And that wraps it up for today. We will be back here again next week with yet another virtual panel, and we hope we will see you then.